Hello everyone, welcome back to the class of TKG physics classes, and I am come back with your another topic for your current electricity chapter. And in this lecture we will discuss the temperature dependence of resistance and resistivity. That means here we find out how resistance and resistivity varies in the variation of temperature, and we find out this form in the case of conductor as well as semiconductor. So students, before knowing this part, at first you have to know the expression of R and rho, the expression of resistance and resistivity in case of drift velocity. And I already derived this expression. If you don't watch, you go back to your video number 3 for your current electricity chapter, go watch it and then come back to this video. So students, what we learned from third video? In third video, we derived this expression, that is resistance R is equal to this one, resistance R is equal to ml divided by n square a tau. We derived this expression. And you know what is R? R is equal to rho L by A. So from this equation you can say ml by n square a tau. Now cancel this part, La. So rho becomes m divided by n square tau. So this is the expression of R and this is the expression of resistivity rho. Now what is m? Write it down. M is the mass of electrons. You can say mass of ions, mass of charge carriers. What is n? N is the number of electrons per unit volume, or you can say electron density. What is A? Is the area of cross section. What is L? L is the length of conductor. And what is tau? Tau is the called relaxation time, or you call it mean collision time. So this is our expression. So from this equation you can say R, this one R inversely proportional to N and R inversely proportional to tau. Here M constant, E constant, for a particular conductor length constant, area of cross section constant. So R inversely depends upon N, that is electron density, you can say carrier density, charge carrier density, and R inversely proportional to mean relaxation time. Similarly, rho inversely proportional to N as well as rho inversely proportional to tau. So this is our dependence. Now we will check the dependence of resistance and resistivity in case of conductor. You know the main formula. This is the main formula. Resistance inversely proportional to N, resistance inversely proportional to tau, mean relaxation time, resistivity inversely proportional to N, and resistivity inversely proportional to tau. Now check it for conductor. What happened for conductor? All of you know, for conductor, when temperature increases, that means the thermal energy increases. So when thermal energy increases, write it down, when temperature increases, that means thermal energy increases. Now when thermal energy increases, the vibration of electrons obviously increases, energy increases, so obviously the thermal energy of obviously the vibration of electrons increases. So now write it down. So this implies the vibration of electrons increases. Now when vibration of electrons increases, that means their thermal speed increases. So when their thermal speed increases, that means the mean relaxation time becomes less. Because the electrons are frequently collide with each other. Why? Because their thermal vibration, this vibration of electrons increases, so the electrons are more frequently collides with each other. As a result, we can say the mean relaxation time tau decreases. So this implies mean relaxation time tau decreases. So you check, when temperature increases, thermal energy increases. When thermal energy increases, the vibration of each electrons increases. When vibration increases, the electrons are more frequently collide with metal ions. So when they collide with metal ions more frequently, obviously their relaxation time tau decreases. Another way, when temperature increases, obviously thermal energy increases, and this thermal energy increases. Now when thermal energy increases, the electrons inside the conductor, inside the most of the metals, what happened? Gain this thermal energy, so they ionized, they gain their ionized energy, so the electrons becomes free. So their electrons, number of free electrons increases, when number of free electrons, that means per unit volume, that means n increases, because when thermal energy increases, the electrons gains this thermal energy and they get their ionization energy. When they get their ionization energy, they can overcome their outer surface and they becomes free. So you just think, when temperature increases, tau decreases. So now you use this formula, relation between R and tau, inversely proportional. That means when tau decreases, R will be increasing. So this implies R increases. And if from this equation you can say, when tau decreases, obviously rho also increases. Think, tau decreases and tau is inversely proportional to R and rho. So when tau decreases, R and rho will be increasing. Now here for this case, when n increasing, you see this one, when n increasing, rho decreases, as well as when n increasing, R decreases. So this implies R and rho both are in decreasing, because n with respect to R and rho inversely proportional. So here for first case, rho and R increases, and for second case, rho and R decreases. So what actually happened here, increasing or decreasing? You just think, for this purpose, in case of conductor, there are large number of free electrons at room temperature, and near about this value 10 to the power 28 per meter cube, 10 to the power 28 per meter cube room number of electrons are there at room temperature. So when temperature increases, obviously n increases, but this increasing with respect to this value is not significant. This is very large amount of free electrons, and this is at room temperature. But when temperature increases, according to our concept, n obviously increases, number of free electrons increases, but this increase gives resistivity and resistance decreases, but this decreases value is not significant. Why? Because with respect to this value, with respect to 10 to the power 28 around, this number of free electrons increases is negligible. So this factor is dominated with respect to this one. So in general, we can say, with increase in temperature, in case of conductor, in case of most of the metals, the resistivity and resistance. So finally you can say resistivity and resistance both are increases. Think it. When temperature increases, tau decreases. As a result, we can say when tau decreases, rho and R increases. Similarly, when temperature increases, N increases. As a result, we can say R and rho decreases. But with respect to this part is not significant, because in general at room temperature, in case of conductor, there is large number of free electrons. So this increasing number of free electrons is negligible. So as a result, when N negligible, this increasing negligible, so this decreasing value is negligible with respect to this one. So as a result, we can say R and rho is increases with respect to increasing temperature in case of conductor, most of the metal. But for some alloys, resistivity and R almost remains constant with respect to the variation of temperature, and these alloys are made for doing some practical purpose. All of you know, when we have to do some practical, we have to do some measuring current, you must have to say that temperature and resistivity and resistance remains constant. That's why our measurement value remains fixed. When rho and R increases for an experiment, in that case our exact results becomes wrong. So for this purpose, we made some alloy with the mixing of some metals, and this alloy have special properties, that is for some alloys nichromes, manganene, constantine, MCN. For these alloys, resistance and resistivity remains almost constant, not exactly, remains almost constant, that means varies linearly, just very slowly for alloy system. But in case of most of the metal, resistance and resistivity increases when temperature increases. Now check what happened for semiconductor. Check it. All of you know about semiconductor, and you say when rho increases, obviously sigma decreases for conductor. Now for semiconductor, all of you know what is semiconductor. Semiconductor, that means conductivity less than conductor but greater than insulator. So same method in case of semiconductor, when temperature increases, their thermal energy increases, as well as when thermal energy increases, their vibration of electrons increases, vibration increases. When vibration increases, this implies the electrons are more frequently, not electrons, here the charge carriers. For semiconductors, the charge carrier, that means electrons and holes. This is an imaginary concept, holes. We learn it in your semiconductor chapter. Okay, in the absence of electrons is known as holes, and in case of semiconductor there are two types of charge carrier, electrons and holes. So here when vibration increases, the charge carriers, that is electrons and holes, are colloids more frequently, so tau decreases, and when tau decreases, this implies R and rho increases according to this formula. When tau decreases, R and rho increases. Similarly, when temperature increases, the electrons, the charge carriers get the ionization energy and they overcome. So when temperature increases, the number of charge carriers increases. Here in case of semiconductor, in general at room temperature, the number of charge carrier very small. But so write it down first. When temperature increases, the number of charge carrier increases, N increases, and this implies when N increases, you see this one, R and rho, this decreases. So here same method. For tau concept, mean relaxation time, R and rho increases, but for number of charge carrier concept, R and rho decreases. Now you think, between these 2 points, which one is more significant? Which one is more significant? At room temperature, in case of semiconductor, the number of n, that is a charge carrier, the number of n is very small, So when temperature increases, the number of charge carriers increases more rapidly, and this increasing happens by doping. All of the doping, that means by adding some impurity with some pure semiconductor, and pure semiconductor, that means there are silicon and germanium, okay, and with the help of some impurity, when added with silicon and germanium, the number of with increase in temperature, the number of the charge carriers increases more rapidly. So when this value increases more rapidly, this signifies R and rho is decreases, and this part is significant in case of semiconductor. This part is not significant, experimentally verified. Experimentally we learned that overall, in case of semiconductor, this resistance and resistivity is decreases with increase in temperature. That means this part is not significant, but this part is significant. Why significant? Because in case of room temperature, for semiconductor, the number of charge carriers is very small, but in case of conductor, at room temperature, the number of charge carriers, that is very large. So for semiconductor, this part becomes not significant, this part becomes significant, but for conductor, this part becomes not significant, this part becomes significant, but for semiconductor, this part is not significant, this part is more significant. So we can say, for overall, in case of with the increase in temperature, in case of semiconductor, R and rho, that is decreases. So when rho decreases, obviously sigma, that is conductivity, increases. So in case of semiconductor, conductivity depends upon the temperature. So this is the variation, the temperature dependence of resistance and resistivity. Now we will check the dependence of resistance and resistivity in case of conductor by mathematically. Okay, check it. Suppose we consider a conductor of resistance R naught at temperature T. Write it down. At temperature T, resistance R naught. Now I am increasing this temperature by amount del T. When del T amount of temperature increases, suppose its resistance increases by amount del R. So when temperature T, resistance R naught, when temperature T plus del T, resistance R naught plus del R. Now this increasing resistance, this del R, this increase in resistance depends upon two factors. This increase in resistance is directly proportional to the initial resistance. When the initial resistance becomes more, the increase in resistance becomes more. And second one, this increase in resistance is directly proportional to the change in temperature. When the change in temperature more, the increase in resistance becomes more. Now combining these two equations, what we can write? We can write dr directly proportional to R naught into dt. So dr is equal to alpha R naught into dt. This equation gives the mathematical form of variation of temperature with resistance in case of conductor. Here alpha is called the temperature coefficient. Temperature coefficient. Now suppose I am integrating this equation, integrate it, dr that is equal to alpha r naught dt. Suppose you know this initial value of resistance, that is r naught, and final resistance suppose you consider r. Initial temperature T naught and final temperature you suppose consider T. Now integration dr, that means r, so use this limit r minus r naught. Here alpha remains almost constant, so alpha becomes outside, r naught becomes outside, integration dt, that is t, and in the place of t you write the upper limit t minus then lower limit. So this equation becomes r is equal to r naught plus alpha r naught t minus t naught. Now take a common, r is equal to r naught 1 plus alpha t minus t naught. So this is the another expression. This expression is always right, but this expression is not always right, because here alpha I am taking this almost constant, not always. Around you can say alpha is constant. Okay. So with the help of this equation we can express mathematically the temperature dependence of resistance for conductor. Now you know the value of R, write down R, that is equal to rho L by A, and R naught, that is equal to rho naught L by A. Therefore there is a alpha 1 plus alpha t minus t naught. So L cancel out, so this equation becomes rho is equal to rho naught 1 plus alpha t minus t naught. This equation gives the variation of resistivity with respect to temperature in case of conductor. Here what is T minus T naught? T minus T naught is indicate the change in temperature. What is alpha? Alpha is the coefficient, temperature coefficient. So this is our expression. This expression gives the variation of resistance with respect to temperature in case of conductor, and this is the gives of variation of resistivity with respect to temperature in case of conductor. Okay. So I think this video is clear to all of you, and in this video what we learned? In this video basically we learned how resistance and resistivity depends with the variation of temperature in case of conductor and in case of semiconductor. So today I ending here, meet you soon in next class. Till then, bye bye.